So last time we basically had the global carbon cycle. We learned how the CO2 gets stored in the seafloor, right, in the ground, and then comes up again, basically. So we know that the luminosity of the sun is increasing. Yeah. Okay, wait. Let's make how do you say that? Summary from last time, something like this. Yeah. Summary. I hope I spelled that correctly. I don't know. Is it summary with 1M? Is it summary with 2M? I hope it's 2M, because I know I took 2Ms, and if that's wrong, I have a problem. Okay. Last time we learned that we have a moderate climate on Earth, despite that the luminosity of the sun is increasing. Okay, so moderate climate. Despite the luminosity is increasing. That's what we learned last time. And we learned why that is. Like an M&M. Is this a spelling stream or science stream? Don't worry about it. It will be both. Automatically it will always be both, since yeah, I'm bad in writing. So I guess I could prepare everything in advance, but I kinda like doing it this way. Let me see if this is better actually. Oh, it's summary outside. Wait, no, that's a wordplay, right? Is it actually a word, summary, like in summer? Okay. So we learned that the global carbon cycle is counteracting, yes? So the global carbon cycle is counteracting. A bad joke. You know, you get banned in this channel for bad jokes. Did you realize this? I haven't done it in a long time though. And we learned a little bit how we did that, right? We learned that the CO2 mixing with the water in a cloud I would think that my writing would get better with time, but it really isn't. It really isn't. So in the clouds, and then the rain is reacting with the rocks, right? So the rain is acid. It got a little bit acid because it mixed with the CO2, and then it's reacting with the rocks. And this way it gets then transported with the water to the seafloor, right? And this way we have a reduction in CO2 and if you have like a removing of the CO2 out of the system, that means we have lesser greenhouse effect, yeah? Greenhouse effect. And this then in the end means lower temperature. Alright, so that's basically the basics, what we learned last time, like in a very short way, said in a very short way. Luminosity from the sun, yeah. Climate is on Earth, yes. We have a moderate climate on Earth, despite that the luminosity of the sun is increasing. Yeah, we could draw a sun here, there. That where it goes inside. Okay, so we had like here the seafloor with volcanoes, mountains, and clouds. And the water. Actually, yeah, okay, there's a little water here. From the clouds, and we had less, right, and here from the volcanoes, it got up, right, and then it went to the cloud, and the cloud reacted with the rocks, and it transported it back to the water. So that's the basics what we did last time. Moderate climate. Half of Europe is melting right now. Yes, yes. I mean, that's our problem, right? That's our problem. The thing is, what we're gonna... I mean, it's important to have CO2. We learned it last time, and we're gonna learn it this time again, that we need CO2 in the atmosphere to have bioproductivity, to even be able to exist, right? And still, and even though, like, CO2 is decreasing actually, we are losing CO2 over time. We are losing it, and even though we manage to increase it so much that we get fucking global warming. Project Venus, make Earth second Venus. Yeah, Venus is nice. Venus is nice. Okay, so at the end, last time we had this, and let me just copy this here. Right, we ended up with this complex system where we had this nice equations here. I put it. The equation, you don't really have to look at the equations so much. They don't really matter that much. But I do gonna just use them as a ground base, because basically every one of these boxes here is one of these equations, right? Like, it's coupled ordinary differential equations. It's like a basic physics. When you have when you want to analyze the physics problems, you're gonna eventually have to develop a mathematical framework for it, and you do this in form of this differential equations. Last time we basically looked at the functions that are on the right side of every of these equations. So, like, the upper one is for like the atmosphere and ocean. No, not the upper one. That is the mantle. It's CM. It's the mantle, and then we have the one for the atmosphere and ocean. Then we have the one for the continents. Then we have the one for the seafloor, the bioproductivity, and the last one is for the kerogen. Yeah. Is it so tiny? Well, we can make. It's really not that important. This is all witchcraft to you, yeah. So they're even coupled, because some of the variables happen to be like more than once, appearing more than once in this, and yeah, we're gonna base a little bit of this. But in general, just you see how complicated it looks. It's actually this complicated and more. So we're gonna go with every box. We're gonna explain every box today a little bit, and basically last time we did a little bit the carbon cycle and some of the functions. We also talked about the biosphere a bit, and today we're gonna go into the sources, the sinks and the fluxes, and in the end we're gonna talk a little bit about protoplanetary disks and why this is actually also important to get a good model, right? I thought you were speaking. Please don't turn on the carpet. Math is not important. Math is very important, but it's complicated, and everyone needs to have like a crazy amount of knowledge then, and we don't want you to study math or like physics to understand this, right? Okay, so we're gonna start with the atmosphere and ocean system. That's what we start with. We go to the next page where we also have the arrow. No. Okay. Sea floor. There. Okay. Good. Put this back. Right? You know what annoys me too is why is there like a... Why is there green? Ah! Why is it green? Go away. Okay. Nice. I love how this points you talk about is in a Warhammer 40k book. What? Is it? You can only do basic calculations and percentage calculations. You don't need more in life. Well, not as a normal person, yeah. Yeah, not as a normal person. I know, I have a dead pixel. Okay, we get the sun here again. And isn't that a beautiful car? We basically say fluxes, yeah? Fluxes, sinks, and sources. That's what we're gonna talk about. Annoying green dogs is annoying. Yeah, it was annoying. It was annoying. Why do you know all the stuff? Because I was reading up about it. I study it, and well, I study physics, and then I have 2 books. You know what? Let me show this you at the beginning, because if last time I forgot it in the end. I don't want to forget it in the end. No. Here, okay, that's like. Yeah, that's the 2 books I'm basing this about. That's where I'm reading it. Wait, damn it. Just that you know. Is it big enough for you to read, or is it not big enough? I have it also when I put it on YouTube, so yeah. Hey Sailor, good morning. I'm learning maybe, yeah. So that's the 2 books I'm basing this about, and I'm gonna show it in the end again bigger. So just because last time I forgot it, I show it right away. Okay, we delete that now again. Yes, delete. Yes, okay. So we're talking about the atmosphere and ocean box. That's not good. No, we take. Actually, no. Just let's take this and just change the color. Okay. So atmosphere. Why is it not changed? Okay. And ocean. Okay. That's what we're talking about first. When we talk about the atmosphere and ocean, the 2 important models we care about is the different model for the atmosphere and the model for the pH value of the ocean. Yeah, that's the 2 models we care about. So, atmosphere model. And the pH model, right? Of the ocean. So what the model that is usually taken for the atmosphere is called something like the gray atmosphere. The atmosphere of the planet is not actually gray, but you have to keep the model. You have to keep the model usable, right? You have to put some constraints on it. Otherwise, you're just never gonna be able to do it. Like we already solved this numerically, right? We solved these equations numerically, and you have to do it somehow. If you put in every little variable, you will never be finished. Hey Demirai, hello, welcome. So the gray atmosphere model says that the absorption of light inside the of radiation inside the atmosphere does not depend on wavelengths and frequency, or I suppose like wavelengths or frequency. It's interchangeable, right? So you know, light has a certain frequency or wavelengths depending range, and in the gray atmosphere model we just say it doesn't depend on it. It does not depend on it. We don't care about this, okay? So absorption of radiation. Does not, oh. Depend on frequency. Models abstraction from reality to make it easier that we dumb monkey understand it. Exactly. That's why there are props. Exactly. That's why we have props. Yeah. So usually it does depend on it. Yeah. Different wavelengths have different opacities for the light. And we make it simple. We say it simply does not. But of course, usually it does. Yeah. It's a simplification. That leaves only the amount of CO2 and water in the atmosphere, like as a factor, and other particles, yeah. So the absorption does only depend on the amount of CO2, water, and other particles. Does it depend? Yeah, we come to this. We come to this too. Maximus is asking the right questions here. Models have to simplify the real objects to systems or systems they are simulating. The devil is in the assumptions. Yeah, the more assumptions, the more likely the model is inaccurate. Exactly. It's basically accumulating. It's accumulating. Yeah. Sorry, I just joined. Are you saying that the model is more useful than measuring refractions or just another tool? The model is a tool, and we use it to make it feasible, to make it usable, right? Otherwise, you wouldn't be able to calculate it because it would either take ages, like the computer would take ages to calculate it. Just we have to make it usable somehow. That's all models are for. Like yeah. And we basically say we use the gray atmosphere model and say we don't care for frequency dependency. We just remove that. We take that factor out of the equation to make it easier. To make it easier for us, right? So what we could say is it's an assumption. To make calculations, model calculations usable. Yeah, we are basically seeing. Yeah, the Mr. Okay, what does the model take into account, and how do we making it easier? Well, we are modeling the whole Earth model, right? It's not about this one thing. We are modeling the whole Earth, the whole Earth system. So we're just like from the last time we looked just about the carbon cycle. This time we look at the whole Earth models. We look like every one of those boxes here is one of these equations from what we had here, right? Can we like one of these equations, and we just look a little bit closer on what that actually contains, right? What that actually contains. We are not actually deriving something. Hey Glitch, we are not actually deriving something. We're just looking a little bit what assumption are we doing when we look into Earth system models. what does it contain, how complicated is it, just a little bit to get an idea how these models work and what we assume and what we not assume, right? Because modeling the Earth system is super, super complicated. And at the end, we just look a little bit more about the fluxes, where they go, where the things go, where the sources are, right? Like this stream is meant for like people who don't have a background in science, okay? So this is just going to be a broad overview. We're not going into like any kind of crazy details here, all right? So just go with me. Just go with me, okay? We are not using actually any data points here. Yeah, we're not actually deriving a climate model. We're not actually doing it, okay, guys? That is, I don't know. Maybe there's an open source climate model calculator we could find and use. That would be great for the next time. If I find something like that, we could do it. So another assumption that is also made is local thermo equilibrium. All right. So wait, how we can this? Okay. Do we have time here? Yeah, I think we have still a little bit of space here if we derive this like this. So the next assumption is local thermodynamic equilibrium, yeah. Equilibrium. I don't know. I hope that's right. We call it short LTE. Okay. Bad writing, I'm sorry. So what this basically means, we assume that the temperature fluctuations are so small that we have a constant temperature around the whole atmosphere, right? So that's what we assume. Assume temperature variations very small, and that just means that we have a constant temperature. Yeah? So otherwise we would have to take into account the whole temperature gradient we have in the whole atmosphere. So we're not gonna do that either. We're not gonna do that either. I think that's nice. And then what Maximus was asking, we also assume like a plane parallel atmosphere, right? So of course the atmosphere is actually has a curvature because Earth has a curvature, right? And we just say we ignore this. We like locally we say okay, locally we say it's flat. Like, you know, Earth is flat locally. If you have like only a thin layer of atmosphere anyway, so yeah. So locally it's flat. So we had like actually a curvature, and then that means light comes from here, right? And now we just assume it's flat. And you see there's a little bit of a difference. Flat Earth confirmed. You knew it. Damn it. Now you know. These are the three main assumptions done for the atmosphere, and for the ocean we have the pH model, yeah. And that's basically the ocean can be acid, right? Neutral, or oh wow, we do it here. Or the last one, alkaline, right? Alkaline. That's the 3-stage, and this basically depends on the CO2, right? How does it compare from today? We would need to know the initial conditions, basically, we put in the model, and we have to assume something. So we have to assume how was the ocean back then, and how did it influence. If you add more CO2 into the atmosphere, it will end up in the ocean, basically, and have an alkaline. Okay, alkaline. These are like basically the two initial conditions. We need to know how is the atmosphere, how do we model the atmosphere, and how was the pH model of the ocean, which is influenced by CO2, right? So influenced. All right. I think that's it for the atmosphere ocean box. We're gonna leave it as that. We see in the box that we have fluxes to the biosphere, fluxes from the biosphere, from the kerogen, like everywhere. Fluxes come from everywhere, and we're gonna shed some light on this. We're going to shed some light on this. Now, I think I wanna. Yeah, this is. Wait, okay. Can I just. Copy that again? That would be nice. Let me copy it. It's not at all copied. That looks nice. Okay, let's try this. Does it copy it? Yay! Alright, nice. Shed some light, funny. Effects of the sun. We had that all the last science stream, guys. That what we more did on the last science stream, how the sun is affecting it. So that today we have like more these parts. All right. Let's see if this works too. Hey, there you go. Nice. So good, guys. So good. So will I do it like this? Oh, nice. Look. Wait, no. There you go. We have some. I don't know how many. How many will I need? I have no idea. Okay, I think we leave it as that. That should be maybe enough. Let's see. Okay, we are back here. 7. I'm curious. I'm also curious if there are any variation caused by differences in the level of the water table. You mean the level of the water? Like how high the water? Like, what do you mean with water table? What do you mean with water table? Alright. Next point. Biosphere. Groundwater. The level, of course, like the water is influencing the climate model, like the amount of water, or more like what's influencing is how many land mass you have, because land mass is important for the global carbon cycle. If you have more land, then more of the carbon gets into pushed weathering, like more weathering is happening to the, that's called the weathering effect, right? The effect of the carbon mixing with the clouds, raining, reacting with the stone, and then going into the groundwater is called weathering. If you have more land mass, weathering will be stronger and it will remove naturally more of the CO2 out of the atmosphere. So yes, water is very important. So biosphere. So for the biosphere, what we need is a biomass model, right? Biomass model. We have like assimilation of CO2 out of the atmosphere. Good day. I'm on time for astrology class. You're a little bit late, but you know, 15 minutes. Oh, it's actually more than 15 minutes, so you're actually pretty late. Water, not so much more snow. Like the snow, the albedo value is more driven by how much, how white the Earth is, right? Astrology. Yeah, we're gonna make some astrology later. Non-zero science stream, yes. Detention. We are taking into account the water level, definitely, but we are not there yet. We're gonna go to that later. Rainbow Earth, yeah, Rainbow Earth. So what we have is here assimilation of CO2 from the atmosphere, ocean system to the biosphere. The refraction, yeah, genau, yeah, that's what we're not taking into account. That's right. Through photosynthesis, right? It's getting taken out of the atmosphere into the biosphere. What we just say, using CO2 from atmo and ocean, we assimilate it. We do assimilate it. So the terrestrial biomass is bigger, way bigger than the oceanic biomass. But actually, when it comes to the rate, like how the assimilation rate, it's actually not that much different. It's only like we have like about 2,000 times of terrestrial biomass compared to the ocean biomass, yeah, compared to ocean. But it only is like 2 times the assimilation rate. That's crazy. Like, that's crazy. I think that's actually very interesting. I didn't know that. I don't know. I mean, that's a real crazy difference. So the ocean is very hungry. The ocean system is very hungry, guys. They really love CO2. They love CO2. They eat it. It's their favorite food. How did I prove that? I don't know. I just trust that I did it. I bet they tested it and looked at it. They took a little bit of ocean and they took a little bit of land biomass, and then they looked how much they ate of it. Yeah, that's the thing in science. Yeah, orgasm efficiency. Yeah, science is like we are standing on the shoulders of giants, right? You cannot learn everything, so trust is very important in science, guys. If you don't trust, then you're not gonna be anywhere. You're not gonna land anywhere. And what we then have is decay. It decays again, right? Back into the atmosphere-ocean system. So we have the decay. Of real organic matter. Hey Lelling! You didn't get a notification? Oh no! Well, trust in the peer review process, not blind trust. Of course, not blind trust. Yeah, you shouldn't just trust what someone tells you. But you cannot just say to anything, well, I have to calculate this myself. I have to completely do it myself. Peer review is not 100% safe, as always, nothing is, but it's a good system. Another detention. Yeah, 2 people late, 2 people with detention. God damn it, guys. We of course add an artificial contribution to this, right? We do fossil fuel burning, deforestation, where we burn the organic carbon. That's what we add to it. That's what we as humans add to this. Is there a naughty corner? Yes, there is a naughty corner. Yeah, in general, we also deposit some of is in the fossil fuels, right? So we have a deposit here in kerogen. Yeah, but I'm not gonna write that down. What we do as humans. This is not about what we do as humans, but we do it. We do it. Yeah. We had the bioproductivity, right? So we have to take into account the bioproductivity per continental area and per the carbon concentration, and we have to take into account the bioproductivity per temperature. So we had the this was a sign for bioproductivity last time. We're gonna continue using it. How did you ever manage without a rocking plant? I don't know, Glitch. I don't know. I know. I'm so happy I found out this rocking function of the share. Okay, and we call this with the A. This is like the bioproductivity per continental area. Then we have the bioproductivity per carbon concentration, yeah. Per carbon concentration. So we need a minimum amount, right? We need a minimum amount. We learned that the last time. That without the CO2, there won't be a certain amount of CO2. There won't be bioproductivity. So we know that, and we also learned that we are losing it. We are losing the CO2, and that will eventually stop bioproductivity. Yeah, Romok. I only now discovered it after 4 years having the share. I just discovered it. Yeah. And also per temperature. Yeah. Per temperature. I think we had 0 degrees Celsius to 100 degrees Celsius, right? And the perfect bioproductivity was about, we assumed something about 50 degrees Celsius. Yeah, actually we are losing it slowly, and that's why the habitable zones actually decrease. Yeah, that's the main reason why habitable zones decrease, because we are losing the CO2. And that's what I said earlier. That is so crazy that we are managing to counteract this completely as humankind. We're just counteracting it. Instead of decreasing, we are increasing it. But if you would leave the system naturally, like that's what basically happened to Mars, right? We are going to lose it. Yeah, we are losing it. So that it's the biomass is then produced by photosynthesis per unit time, and we also have a dependency on how long the carbon is stored in the biosphere, right? If you write down the formula, so this is how the formula looked like. Like this is T is meaning the time here, right? So this is the bioproductivity, all this together, yeah, all this together in the model. And C bio. Then we had like this is the resident time of carbon in the biosphere before it goes back to the atmosphere, right? And this here is just the amount of carbon stored in the biosphere, right? So that, and this is the bioproductivity, right? So this goes in the model for the bioproductivity. Per temperature as in, yeah, like, yeah, okay, like, it's maybe, I should have written it differently, Maximus, but it's basically meant that we have this range of temperature where we have bioproductivity and there's a perfect temperature in the model we assume for bioproductivity, and outside of this temperature range there is zero bioproductivity. Global cooling, humans are like, nope, we are making Earth second Venus, yeah. Okay, make bioproductivity, not war, exactly. So it depends, like, just what does it depend on? Let's just say we have photosynthesis, right? This is basically radiation, we need radiation. And also for radiation, again, we can have a too high amount or a too low amount. We need the perfect amount, right? We need the perfect amount. The surface temperature, the CO2 concentration, CO2, and water supply. Yeah, water supply. Okay. That's it for the biosphere. That's it for the biosphere. Bioproductivity is basically the amount of biomass that is produced by photosynthesis per unit time and continental area. Yellowstone, you think you're going away from global cooling? Hold my beer. Yeah. Okay, that was the biosphere. That's messy. That's messy. Damn it. Damn it. Okay. Do we? Okay. I like the feature, but I should leave more room. Okay. Do we get that here? Whoa. Nice. Nice. Now I have my messy writing with me. So now we get to the Kerogen box. Okay, we deposit a little bit from the biosphere in the Kerogen, right? So it's like it's organic carbon in rocks. So organic carbon in rocks, like coal, mineral oil, right? There you go. It's like dispersed, and it's not much. It's not much. HRG. It's like only 0.1% of the dead biomass or something like this that is returned. That is not returned back to the atmosphere, right? Yeah, to the atmosphere and ocean too. Isn't 35 too many in one classroom? And this accumulates, right? Kerogen is actually, it accumulates during Earth's history, yeah. it gets stored. Only 0.1% of the dead biomass is not returned back to the atmosphere ocean system. It gets stored in the kerogen, and it accumulates over Earth's history, right? You have a question? Oh no, oh no. Of course, ask the question. I hope I can answer it. Is it the dinosaur fossils that we found? Well, they're dead biomass too. Yeah, they're dead biomass too. No, it's called mineral or something like this. Anything like this. We also have to take into account the residence time again, right? There is weathering, like there is kerogen weathering. And it's I don't know. I have no idea of that. Yeah. So you have kerogen plus oxygen, and that somehow produces CO2 and something else, and that gets returned into the atmosphere. Yeah. Isn't oil like 99% plankton and sea microbes? I have no idea. Like, I have no idea. That's I have no idea. My wife is a prof, is a limit of 25. The largest my class got in high school was 33. Yeah, in uni you are massive. In university you have massive. You have like over 200 people or something like this. That in university, right? So in this equation we need to take into account the transfer in this model of the dead biomass into the kerogen, and we also have to take into account the resident time of the stored carbon in the kerogen. So these are the two factors that go into the model, right? The two factors that go into the model. The kerogen goes back to the atmosphere with a decay. We said that here, but it also has the kerogen weathering we just talked about, right? So we just call this weathering again, and that's it. That's all the fluxes that we have to take into account. So the model so far, we have to take into account the atmosphere and ocean, the fluxes to the biosphere, the fluxes from the biosphere, the fluxes from the biosphere to the kerogen, and the flux from the kerogen back to the atmosphere and ocean. That's quite a lot for the model already. Right? Teacher. Yes. Shows hand. God damn it. This is a waving hand. That's quite a lot for the model already. And now we're gonna get to the continent. Wait, is this for the EMA? What? Okay, so no, can we do it? Yes, he did it. They use all kind of the models they use. They're like different kinds of models. In the end of the day, it's complicated shit. I mean, this is just where is it? One way to do it, right? This is just what I read, what I took out of the book. I'm sure there are other models that don't use other kind of differential equations, other kinds of approaches. Like, this is just like basically what you have to take into account. The source stream is complicated shit, yeah. It's just conceptual. This amazing software, I know the software is amazing. Let's go to the continents, guys. Let's make it more complicated, okay? Let's make it more complicated. Continents. It's not complicated enough. We have to make it more complicated. It's not complicated enough. Okay. Continental growth model. Let me try to write it good. Continental growth model. I like complicated, you should see my girlfriend. Yes. Yes, Balleur. And what we mean with the growth is the growth for the continental crust, right? Growth of the continental crust. We assume that we had early on less continental area. Let me see. I think I prepared a picture for this from the book because I didn't want to draw it. Use, there you go. That's from the book. I'm gonna show it in the end again. That is the models they have for the continental growth at the moment. You believe that? God damn it, guys! Okay. So we assuming, of course, every model we assume we have some basics. We are relying this assumption on, but we assume, yeah, that Earth had less continental area at the beginning. Yeah. It's not the oceanic crust. If we talk about continental area, we have to be careful. We are not meaning the oceanic crust. The oceanic crust is something different. We just really mean continental area. Yeah, this exactly. We're meaning the surface area of the land. We do not talk about the ocean surface. Does continental growth equate to oceans dying out? Yeah, if you have like if the flux for the mantle, we're going to talk about that later on too, takes too much of the water away, then of course water is gonna reduce. Yeah. So we have more land even though ice is melting. Yep. Basically over the whole time packs, like we assume that we started out at some kind of water world, and you can see it here. All right. There's also the model for continuity, right? But in general, what is very important, we're gonna make this in red, and why continental area is so important, yeah? It's a larger continental area. Area equals to larger weathering rates. A larger weathering rate will remove more CO2 out of the atmosphere and store it in the ocean, so it takes CO2 away and stores it. Right? So that's why we need continental area. So if you have less continental area, you will have more CO2 in the atmosphere. Long of term. There are two main theories of what happened to the continental area. Yeah. Two main models. We see here that it's actually 4, but we have 2 main models. One is that it formed very early on and recycled through the mantle throughout the years, and that way it stayed constant. It stayed constant, and that's like the sea line. Yeah, it just always stayed the same. It did not increase. It stayed the same. That's one. Yeah, methane, and that's the thing. See, we can always make it more complicated. You can always make it more complicated. So some models don't even take that into account, but of course we should. Like the biosphere in general, when you make this model, biospheres are underestimated in a large amount. How much they contribute. It's crazy. Then how come ocean can light on fire? Okay, so the first is formed early on. In history. Recycled through the mantle. And thus stayed constant, right? This is the sea line. That is the sea line that is marked with C. You see in the graph here, right? And the second assumption is the crust grows with time, with time, without recycling. Yeah. You see A, B, C, and D, and the D line actually, like B and C, you see 2 different lines for the growth. Yeah, for the growth. So the B is pretty linear. The A line looks a little bit delayed. You can see with the A line that the continental crust formed later. Yeah, later than on the B line. And then the D line, yeah, the crazy line here. This comes from geological investigations, yeah, from the North American and Europe continent. It used to be one continent in history, and that's what they like concluded from investigations of this. Yeah, that there was one landmass, and they said it grows episodically. Yeah, so what they found is that it probably growed at least like some mass on Earth, like some of the continental crust was growing episodically in Earth's history. So depending what you put in the model, it's gonna change the outcome, right? It's gonna change the outcome. We probably should add the fluxes here. So the continents, we have the weathering here, of course, right? This is the weathering. To the ocean, towards the ocean. Then here we have basically, this is basically rain. Let's call it rain. It's shorter. It goes into the seafloor. So this is the main. This is the 2 main. Can we make it better? Right. There's also hydrothermal reactions, alright. Not just rain. Then ice ages reduce the continental growth by the ice pushing down on the continents. For example, Sweden is still rising up as a rebound from the glacier that used to press it down. Yes, of course. That will definitely effect, and I think that's what you probably see here also with the periodical growth, right? That there's some effects that can influence the continental growth. But I guess overall it's still constant, right? It's still growing constant. As you said, still rising. Still rising, so it's still growing. Yeah, there are some hydrothermal reactions happening in the ocean, basically. No, I mean it doesn't look linear. I mean, if you look at the model from observation, so B is the linear model, right? And you see that we are pretty much on track from the observation. Probably, like, you see, this is 0, right? This is where the 0 is nowadays. And now we don't know how the future looks like. That we don't know it. It could be anything. These are just assumptions. Right? Maybe it grows episodically again. Like maybe it makes this again. Who knows? But we have to assume something. And we put this, we put the assumptions apparently like this in place. Monotonous, linear, somehow. Maybe it's not true. Who knows? It's the future. We have to predict it. The thing with the model is that we put all the initial assumptions in the equations, and then we can see if we get the right result, right? That's the good thing in this model. You just make initial assumption, put it in the equations, and then you see, did we calculate it right? If we look nowadays, did it right? We had like, this is the equation at back then, yeah, when at the start of time, and we go to nowadays. What do we have? Like 4.5 gigayears today, and we see, did we do it right? Either we didn't, we come to a wrong, or we get a check mark, and then it's right. I mean, who knows? Okay. Yeah. Seafloor. Let's talk about the seafloor. Make a model more complicated. We don't have enough stuff yet. So we need we need more complicated things, okay? We only have that much now. We need more complicated things. Is that enough? I feel like I don't have everything. Let's see. I do have everything. So good. You're extrapolating on data points from the past. Yes. Yeah, you don't know if the prediction, but you can check. Like, you can check if you arrive at nowadays. Demara, you can at least check if the predictions bring you to today, right? If you reach the data points from today. Sometimes you get a check mark, but you were still wrong about why you were right. That is true. That is true. That is very true. Okay, seafloor. Yay! So, when we talk about seafloor, we mean the oceanic crust. Oceanic crust. And the sediments. Methane category progress. Now. So the weathering products get transported through the rain to the seafloor. And there we have the hydrothermal reactions. So it's also an additional thing, basically. Isn't the seafloor? Well, it has a different. It's a different kind of thing. Yeah. Okay. If we let's make this so. Let's actually make it a different color. So if you have like the seafloor here, it's basalt, right? Let's call it basalt. Apparently that's what it mostly is. And then we have the like we have the Earth here, right? The continental crust is here over the seafloor. It's different material. Okay. Wonderful drawing, perfect drawing. It's absolutely beautiful, guys. So what also happens is the hydrothermal reactions and fluxes, yeah, makes an additional sink. So first we have the sink, of course, that comes from here, and then like there's CO2 dissolved in the ocean, and it reacts with the basalt from the mid-ocean ridges. Yeah, this is a mid-ocean ridge. It's degassing. It's degassing CO2 and water, and the CO2 then reacts again with the basalt and then goes back. It's an additional sink, basically, an additional sink towards the weathering sink. Yeah. So we have here a hydrothermal reaction, and here the weathering. So here weathering, and here the hydrothermal reaction. So, cool mustache drawing. Is the seafloor like a bedrock in Minecraft? I never played Minecraft, so I don't know. Okay, we're not gonna go into any more detail on that, because that's the two fluxes we care about. That's the two fluxes we care about, right? The sinks and the degassing. And we talk more about the degassing when we talk about the mantle, so we leave it at that. We have from the sea floor, basically, it's more, yeah, it's coming from the sea floor, so there's like accretion here, accretion happening. Accretion. God damn it, I can't write. Can I do that better? Let's see. No, let's see if I can do that better. That no one can read this, guys. Okay, wait, we make it like this. That is terrible. Okay. We leave it out. We have to remember that this is the accretion back to the continents, right? Through tectonics. The magnetic field of the Earth is very important, but since we talked about that last time, it's very important to keep the atmosphere, right? If we don't have a magnetic field, we're gonna lose all the atmosphere, like Mars. Mars just lost the atmosphere because it doesn't have a magnetic field protecting from the solar winds. The flux, what is flux? Flux is basically just in this case, amount of something, mostly CO2 in this case, right? Stored in various forms, going in one direction or in another direction. Yes, you are in school today. The drawing looks like an ad for pimp. People say weed makes you stupid, but I understand some of these words. Like flux in Dwarf Fortress? Yes, exactly like this. Exactly like this. Absolutely. Completely right. Exactly like this. Alright, let's go to the mantle, because it's okay, shit. Damn it. Wait, no, we can just do this, because did we add something? Oh yeah, we added something. So we draw it again. The mantle. The mantle. Mantle is a very complicated stuff. Very, very complicated stuff. Any effect that appears to pass or travel. Yeah, Venus had probably shit ton of dentin. Yeah. So what we need for the mantle is a thermal evolution model. We don't have enough models yet. So we add a thermal evolution model. Ha! So we need more, yeah. It's basically the mantle surface water interaction, right? Lelling, Carl Sagan. This is lost on me. Who is that? Stop gifting me subs, Lelling. God damn it. Well, I mean, Mercury is very close to the sun, right? As a side, no, I don't need to know that. I don't need to know that. People always think that you know anything. Just because you study science, they think you know everything. You know what I realized? That people who actually don't study science know more about the people than the people themselves. Because you're very narrow. You're very narrowed in one field, right? I see. Nice emote. I'm sorry to disappoint you guys. I'm sorry to disappoint you. So what this is basically is, I feel like I want to use this button. White, yeah. Mantle surface. Water. Interchange. Stop gifting me subs, spots ever spoken by a streamer. Yeah, man. Lelling is poor and doesn't stop gifting me subs just because he can gift subs to funny names like Chris Robber. He was Neil Tyson before. Oh, he was? Okay, I have no idea about that, guys. I don't know, sorry. Stop scamming the poor Slovenian. I know, right? Okay, the interchange is happening due to plate tectonics, yeah? Due to plate tectonics. There we have it. He was one of the NDT mentor. Look, guys. Stop it! God damn it! No lelling. No. Okay, first thing, degassing. Oh, no, I didn't want to do that. Okay. Okay, let's just degassing. Right. That is here. That is happening here. Enough. Yes, enough. So the present Earth has the water mostly expelled from the mantle, right? It degassed the water to the surface due to volcanism and the mid-ocean ridges. It degasses the CO2, but it also like degasses the water mixed in the mantle, right? I think we could probably... Should we just draw again? Yeah, I feel like we just draw again. So what we have here... Can we do that here? Okay, let's actually... Nah... Okay. Let's try that. So we take apart. This is like a pie. This is a pie from the Earth's crust, alright? It most likely degases methane too. Yeah, I mean if there is methane in the crust, in the mantle, it's gonna it's degassing every fucking shit that is in there. So we have here the core, yeah, core. Core. And what we have here, I think we take this again, right? Remember, we have here the seafloor. This is there we have the mid-ocean ridges. We had that before. And we have the degassing happening here. Degassing. But what we also have is regassing. Yes! Regassing. Not only degassing, yes, we have also regassing, guys. From the seafloor. It's regassing. Yeah, so the water is lost from the surface through the mantle. Mostly through to plate tectonics, right? Yeah, it's getting lost again. So we need this balance. Eat less beans. And we also have like a temperature here, right? We have a temperature of the mantle, and which is here decreasing due to radioactive decay. And it releases, it heats the seafloor, and because of the heating of the seafloor, it does the degassing of the CO2, right? So it heats seafloor, and then this releases the CO2. So if we're gonna like lose the heat, apparently we're gonna have less degassing over the time, right? It's gonna get eventually stop. We need what we need is basically a balance between the degassing and the regassing. And this process is basically determining the amount of water we have. If we're not taking account any ice melting or something like this, but the water level is basically related then to the balance of the degassing and the regassing. So if we wouldn't have the degassing, the carbon would just stay inside, right? It would just stay in the crust and would never get out again. If we were recycling the CO2. Well, we don't need to keep it exactly as it is, but it's affecting the habitable zone, right? So what we learned. So this is important for the habitable zone, right? We learned that the continental area is determining how much CO2 gets taken out of the atmosphere inside the crust, right? Inside the crust. If we have less CO2, the temperature, the greenhouse effect is less. if the greenhouse effect is less, we're gonna have a lower temperature, right? That's reducing the habitable zone. So meaning water worlds have a wider habitable zone, have a wider range of the habitable zones, because they have more CO2 in the atmosphere. This is weird. This is so weird. Because we're talking about Earth and how we're increasing the CO2 and how this fucks up our system. And now I'm sitting here telling you that we need CO2 for bioproductivity, and if we don't have enough, we are not in the habitable zone anymore. I mean, this is just, I think this is weird actually. I don't know if you see it like this, but I do see it like this. I think it's crazy actually. So, for a planet to be habitable, it needs to accumulate enough water. And then it also needs to regas the water out of the mantle, bring it to the surface, right? So that's basically, so what we can say, that a rocky world will have a smaller habitable zone. I just call it HZ, yeah. Due to the increased weathering. And the water world has a wider habitable set, habitable zone. Yeah, has a higher possibility to be habitable. We need nitrogen, right? We need everything. Water's a great stabilizer. Yeah, now you assume like you create a planet and it accumulates enough water, but it doesn't have any plate tectonics for the degassing. The water never leaves the mantle, it will never have an ocean, it will never have bioproductivity. This is making me want to play space colonization games. Teacher, yes, yes, please. So basically what we should write here though, the outgassing was higher in the past. The degassing was higher in past and will decrease. What had happened? The moon disappeared, tide stopped in terms of weathering. Yeah, in terms of weathering, not so much. In terms of plate tectonics, right? I assume that when the moon goes away, it would have an effect on the plate tectonics. I mean, we don't have the tides anymore. I don't really know how this would have an effect. It would definitely have an effect if we don't have tides anymore. But I would also assume that it's gonna affect plate tectonics, and plate tectonics we just learned are very important. So I don't really know, it's just what I would assume. So the CO2 released from the seafloor is the balance against CO2 released from the forest on land. Yes, exactly. So we're gonna remove the CO2 due to the weathering process on land, and the release of the CO2 from the seafloor, it's basically the balance, exactly. And the more land we have, the more it gets removed, and the less land we have, the less it gets removed. Because land is very important for the weathering process. Yeah, that is it. Okay. That's the mantle. I guess we could write that here for the. So this is the degassing. This is the regassing. And here we have the accretion. I try it one more time. Accretion. G10. Okay, and this is wait, why is that here? It's probably the hydrothermal directions. Yeah. All right, that's for the boxes, guys. That's for the boxes. So we have now seen all the boxes: the atmosphere, ocean, the biosphere, the carrying, the continents, the seafloor, and the mantle. We have seen overall what's important for the models, what has to go inside, and we see it's kind of very complicated, right? And one other initial assumption we have to do is how did our Earth start out, right? If we want to know how were the initial conditions for Earth, the drawing is nice, right? Then we have to know how did, like, it would be helpful to know how did Earth like came to be, what were the initial conditions on Earth. You know what? There, it's gone. It's gone. Wait, no, I have to actually, I have to at least take this. I mean, the moon is leaving us. So eventually, why is it not drawing? Eventually, we will find out what happens when the moon fucks off. We will find out, guys. We will find out. Because the moon is leaving. Okay. So, what we gonna... Ah, we're missing something. Never mind. So, initial conditions. No, actually no. Let's call it protoplanetary disk. Now, we now talk about the protoplanetary disk. Protoplanetary disk, right? By moon, yeah, by moon. Is the Earth going to end up like Mars one day? Hard to say, actually. It depends a lot on us. It does depend a lot on us, but yeah, it's yeah, like eventually we probably will lose our stuff. Yeah. Don't leave us, moon. He's gonna leave. We can do nothing against it. Why is it leaving? It has something to do with the... How's the English word? Fuck! I don't know the English word. What? Let me look it up. Momentum. Angular momentum. Okay. Fuck. God. How do I forgot that? Damn it. Angular momentum. Yeah. It has something to do with angular momentum. It has to be in balance, and because there's friction, it's not actually in balance. I'm a bit behind now. I can't read it all anymore. I can't read it all anymore, guys. When the Earth cools off, we become Mars. Yeah, that's the thing. When the Earth cools off, there won't be planet tectonics anymore. So the whole system is gonna break down, right? Yeah, the tides make friction. Friction changes how the angular momentum of Earth, and we have to compensate that because it has to stay. The angular momentum of the whole system has to stay the same, and that the moon is compensating this by leaving us, right? So the angular momentum stays the same. Conservation of angular momentum, yeah, exactly. Your question were above. How come the moon is a perfect distance from us to produce a perfect solar eclipse at the same exact time that there's a technology civilization on Earth? Conspiracy. Interesting. The answer is very simple. Okay, but I'm not gonna tell you because I keep it a secret. What happens when the moon flies well? Becoming a planet? Will the Earth survive? Good question, Romhawk. That's no moon. That's no moon. It's a space station. Yeah, maybe Mars gets it. Who knows? Maybe Jupiter's gonna catch it. Maybe Jupiter is gonna catch the moon. Yeah. Okay. You know what? Let's start off with a picture. So you all shut up. Yeah, Jupiter, it's my moon now. This is a picture of a protoplanetary disk taken with the ALMA observatory in the millimeter wavelength range. Yeah, what we are seeing here is the millimeter wavelength range, and what we are seeing is dust. We are seeing dust. So yeah, we wanna know the initial conditions of Earth. We don't know how Earth came to be. So what do? We look somewhere else. We look somewhere else and assume, hey, that's how it happened there. That's how it happened with our Earth, right? to know the present state. So we can only assume, and the assumption is that there is a protoplanetary disk after a star is born, and the protoplanetary disk is basically a rotational disk made of dense gas and dust. Yeah, so they found one. They found only not one, they found more, but we're gonna look at this. So, okay, we're gonna write down what the protoplanetary disk is, okay? It's a dense, the star, let's say we start with the star, is surrounded by rotating dense dust and gas. Alright? And surprisingly, it's not uniform. It's not, if you can see here, it's not uniform. It has gaps. It would be dope, but you with a solar moon, it would be really dope. Okay. It's not uniform. That's what they were always wondering, like, how is it that when, like, if the dust is basically falling together, forming like little rocks, forming like asteroid-sized rocks, normally due to the friction in the disk, the dynamic should be in a way that the little rock that is forming is eventually falling into the star. That's the general assumption. And the question is, why is this not happening? And one reason why this is probably not happening is, as we can see here, that it's not uniform at all. That there are gaps in this disk. And this giving it enough room to not fall into the disk via dynamics. Yeah. Okay. Non-uniform has gaps. Density gradient, yes. And also something very interesting we see here is this line. You can see this line. And this is something called, apparently, that what we're seeing here is the snow line. It's called the snow line. Sun is expelling energy, like explosions that would push away smaller objects. No. Sure, very violently windy stars, but this is just a protostar. That's not a real star yet. Yeah, the thing is, but we don't actually know. It's so complicated. We have nothing to actually really find out what's happening, and there's more to it. This is only showing the gas, the dust. We will later show that there's also gas, and the whole kinetics and dynamics. Actually, we're making assumptions out of our asses, right? This line here, can we just draw on it actually? Yep. So this line here, wow. Ooh, can I? Okay. You know what? I just keep it. I keep it at this. So, you know, this gap. It's a snow line. Snow line. I think it's the Eye of Sauron. Yeah, it's the Eye of Sauron, exactly. Creeps in the side door, sits down, knocks his hand on someone's ring, spills this on the floor and says sorry too many times. Hey ninja, welcome. Okay, science doesn't know but won't admit it to make up some bullshit. Exactly. We're making up something, then we make observations and see if these assumptions could be true. So what happens with the snow line? Below the snow line, there's water is only vaporized. It's too hot. Like it's a fire in the snow, right? Imagine a fire in the snow. Either you have snow around it or you have the fire. So, and behind this, the dust is just the particles and dust get frozen, and below this, it's heated so much, the water is only vaporized. Normally the snow line would be very closer to the planet, but in here, it got pushed out so much that we can actually see it. Yeah, that we can actually see it. So the leading model is basically like I think I have another one. Right. Yeah, this actually is better. I should have shown this right away. So there's a better one. Okay, right. Let's make this smaller. There you go. So they observed more than this, right? Miss Teacher Person, yes. Isn't most of the metals ending up inside the star? I don't know. We have a lot of metals in our Earth, right? What is most of metals? Like the star is a larger mass, so there's a large of metals. If something is a larger mass, it probably consists of more metals. Metals kill stars? No, why should metals kill stars? At the beginning there were no any metals. There were no metals at all. Only the supernova started to giving us metals, and then we have a higher metallicity in the now produced stars, basically. What does it look like in 3D, or is it because the sun's rotation is flat to observations? Actually, they have found systems that are not really flat. They have found systems that do not appear really flat, but have like a rotation in various ways, yeah. Well, I mean, the sun is way larger. Like, is this per unit mass, or like, I don't know. The sun is way larger. Of course it has more iron, but I don't know if it's per unit mass or just in general. Miss Teacher Person? Yeah, I know. Is it safe to assume not flat but tending towards flat? Yeah, safe to assume. So the leading model is basically 4 rocky worlds. This is like 4 rocky worlds, okay? We're not talking about gas giants, but we have like a gradual accumulation of gas and dust. Right. So they form grains of dust. Grains of dust then form tiny rocks. Tiny rocks. The tiny rocks form asteroids. Right. The asteroids then form planetesimal objects. And they then form the planets. Alright. It's a hierarchical structure, and that process should actually take many million years. That's what thought. We thought it would take many million years, but it's actually way faster because they found apparently protostellar disk that are only like 1 million years and already have this ring structures inside. What is to be assumed like some kind of rocks that making the structures. Right, but I read that once the sun starts fusion iron, it can't sustain the fusion reaction and starts a death spiral. The sun is a low mass star. It's pretty low mass. It will just end up as a white dwarf. It will die out because it cannot sustain the fuel reaction anymore. Jupiter cleared up the space, yeah. Something against gas giants? No, gas giants are fine. We're just not talking about them. I just say that the sun is a low mass star. The sun is a low mass star. That's what I said, Ramog. So they've surprisingly found out that like the system's only 1 million years old, already have the structures, and that's probably way faster how these planets are getting produced here, yeah? And we see these gaps, and they're basically providing protection from falling into the star, because that gives them more room. We have to, yeah, okay, I have another pretty picture for that, basically. There you go. I feel like I make a new site. I make it here, so you can see it properly. So we watched more than just one system, and you see there is a variety of systems. But at the end, they also like have these gaps. All of them have the same features basically. And don't forget, we're only looking at dust. We are only looking at dust, okay? Still, even though we saw this nice dust structures and thought, hey, nice, looks good, right? Eventually, they was thinking like, hey, let's find out about the gas. Let's find out about the gas. And this is what I found. It's a spiral gas structure. And basically now they're like, it's probably not as easy as we thought it is. And it's probably like, the rings are going like very far out, yeah? Like 3 times Neptune or something like this. And the gas structure is going way more out. Like the blue thing now is the gas, right? Yeah. The yellow is the dust and the blue thing is the dust. And you see how small this is. It's only like in this little. And the gas, of course, also affects the dynamics. Huh? It affects the dynamics as well. Yeah. It's not easy. It's not easy, but it's very interesting, and I can only recommend if you go to ALMA Observatory. There, I wrote it down there. It's you can read a lot about the protoplanetaries there on the website if you're really interested in that. It's a really cool topic, in my opinion. For me, it's one of the most interesting topics. I didn't want to do it the main topic. Maybe I do a main topic on that because I really think it's super interesting. But in here I just wanted to show you, because it's already 2 hours now, that the initial conditions, to get the initial conditions, how Earth came to be. And of course, at the beginning, Earth would have made like a liquid magma and wouldn't have any water and stuff like this. It's not so easy to conclude to, because we don't actually know. Yeah, we don't actually know. And we're gonna have to observe more and study the dynamics and the structures in this. Protoplanetary systems. Protoplanetary systems. Yeah, but it still has an effect on it, right? Like these gaps, we assume they're there because a little structure has formed and clearing up. But it could also be another physical progress, right? Yeah, these are planet forming, yeah. This is a whole system. No, this is a whole system. Like this is the central star, in the middle is the central star. And this is the disk of hot dust around it with gaps and the snow line. 2 hours, planet isn't even formed. Does dark matter play any role in planet formation? I don't think so, because dark matter does mostly play a role for the whole galaxy, right? But then again, we don't really know that much about dark matter. Dark matter is a concept. We don't even are 100% sure it's true, right? So yeah, guys, it's 2 hours and I think I have talked enough. I would have thought I'm quicker, but I wasn't. So this concludes science stream number 4. I'm gonna definitely make a stream about dark matter at one point, 100%. But I wanna keep it on topic on astrobiology. So next time we are done with the Earth system, guys. You will be on time next time. Yeah, I'm gonna upload this to YouTube. I'm gonna do that now for people to re-watch. 2 hours flew by. Enjoyed it very much. Thank you very much, Dr. Gisbank. Did we talk enough? It's very, yeah, I don't know. It's very hard to talk for 2 hours about science. That's just the thing, guys. That's just the thing. At least for me, it is hard. Put that here. So yeah, guys, I try to make a new science stream soonish. Maybe next month. Who knows? 2 hours and no crash chips. Yeah, no crash chip, exactly. I hope it was informative. I hope I could cut a balance between being too boring for the people who know already everything and the people who don't know shit. Yeah, if it was a citizen stream, I would be just up right now. Let me tell you one supporting fact already. I won't stream tomorrow for reasons that will be disclosed. I will have a Saturday stream next week, so I will not stream tomorrow on Monday. Just that you know. I'm sorry, but it is what it is. I cannot stream 6 days a week. That's not possible. 3 months later, yeah, Pax, I want to make it quicker. I hope it will be faster, yeah. Foundation, yeah. Yeah. So guys, thank you so much for being here, for listening to me rambling. It was very good. Thank you so much. I hope I'm gonna make a next science stream next month. I'm gonna try to kick my ass because I'm having a lot of fun doing them. Yeah, no stream tomorrow, like the biggest thing. I'm gonna make an announcement on Discord. I had so much fun doing them, so I want to do them more often. For reasons. So have a nice Sunday, guys. Have a nice rest of the Sunday. Some of you have a bit more of the Sunday. Some of you, the Sunday is already gone and have to get up to go to work tomorrow. I'm sorry for you. Bob Ross glitch. I can only recommend Bob Ross. Why are so celestial bodies irregular shape or others are spherical? Most are You mean the galaxies? Oh, that's a whole other topic, but mostly is like spherical somehow, right? But I want to conclude now, so I'm very sorry. I will not go into more detail in that now. I'm on my end right now. So, guys, have a great rest of the Sunday, or have a great start of the Sunday, whatever. And I hopefully see you again sometime. Live long and prosper. Bye bye.